And maybe for those who did not do or forgot about the bachelor course about negative feedback, it is maybe good to have a little recap on negative feedback and how we view upon negative feedback and how we are going to use it. So feedback. Feedback is a method to establish an accurate transfer from a signal source to a load. And how do we do this? Basically, there's a very simple recipe to make a feedback amplifier. What you have to do is you have to generate a copy of the source signal from the load signal with a feedback network. And how does this feedback network look? Well, the input signal of the feedback network is then the load quantity of interest. So if you want to make a voltage amplifier, then the load voltage should be delivered to the load, and you want to generate a copy from this load voltage, a copy from the source from the load voltage. So the source quantity, let's say if you make a voltage amplifier, it's also voltage in, so you have to attenuate or make a copy from the load voltage and then compare it with a source. That's what we are going to do. So the output signal of the feedback network is the accurate copy that we want to have of the signal source of interest. So let's make a overview of what kind of amplifiers you can build. And I just made a very small matrix to show you this overview. So we have a source type that can be voltage or it can be current. And we have a load type and it can be voltage or current or both. If you want both an accurate voltage and an accurate current to be related to the source quantity, then you want to have an amplifier with an accurately defined output impedance. And if you want to have a nice relation between the source current and the input current and the input voltage of the amplifier, then you want both the input voltage and the input current related to each other, which is an accurate input impedance. So which transmission parameters are then involved? So if you have source voltage, then we are talking about parameters A and B because they have voltage as the input. A, voltage in, voltage out. B, voltage in, current out. If you want to do voltage source at the input, then you need to compare at the output of your feedback network, of course, with the source voltage. And this is done in series because comparison, subtraction of two voltages should be done by placing the voltages anti-series. That is what we have discussed in the bachelor course. If you are not familiar with this way of thinking about negative feedback, please go to the homologation program because that's a lot of information about it in that program. Let's go to current. If we current source, then we are fixing parameters C or D because C relates input current to output voltage and D relates input current to output current. In order to compare currents at the input, we need to have a parallel comparison because currents are subtracted from each other by placing them anti-parallel. If we have voltage at the output, again, we have A or C because A is input voltage to output voltage and C is input current to output voltage. What do we have to do at the load then? Of course, sense the voltage because that's what we want. So we have parallel sensing because the voltage should be measured in parallel with the voltage source. If we want to have a load current at the output, then we are talking about parameters B or D. B relates input voltage to output current and D input current to output current. And again, if you want to sense the load current, you need to do series sensing. So this is the overview. This is basically what we do, how we construct negative feedback amplifiers, all kinds of negative feedback amplifiers, and we have done this in the previous course. Now, in this course, I mainly want to focus on the conclusions that we draw on the last course and see how it works by building amplifiers or single-stage transistor amplifiers with it. So if we have this copy of the source signal, Then we need a controller, which is called a controller or an error amplifier that generates a load quantity and nullifies the comparison result. So basically, it has a huge gain to nullify the comparison, to build from almost zero comparison results the output that you want. Feedback stages. So we are now going to talk about local feedback amplifiers, which is amplifier stages that have only one transistor or one transistor stage as controller. So we will distinguish 3-terminal controllers and 4-terminal controllers. First, the 3-1. So if we have 3-terminal controllers, we can make the ideal controller would look like this. It would be a nuller of which the input port and the output port, so the nullator and the norator, have one connection in common. And of course, you cannot build all amplifiers with it. This is, I hope you remember from the previous course, but you can make a lot of amplifiers with those, and that's why it is interesting. It's also interesting because our transistors have 3 terminals. So the NMOS CS stage, like this, is a very simple implementation of this nuller. Of course, it is biased, but we omit here the bias sources. Or the PMOS, you can also do it with a PMOS. Or another 3-terminal solution is the complementary parallel CS stage. 4-terminal solutions also. 4-terminal we have seen by using balancing techniques, anti-series connection, we can convert a 3-terminal element into a 4-terminal element having almost the same properties, but odd characteristics. So now this is the ideal controller, we call it a nuller, and these are the 2 solutions of anti-series with P devices and N devices. Of course, you can also use a 4-terminal controller for a 3-terminal application, but not the other way around, but this one you can. Types of feedback. This is also a recap from the bachelor course. The types of feedback that we have. We talk of direct feedback if we are sensing the load quantity of interest and compare with the source quantity of interest. This is called direct feedback. Indirect or model-based feedback is if we sense something which is related to it. So indirect sensing of a copy of the load quantity or indirect comparison with a copy of the source quantity. If your copy is not perfect, then of course this will be of less quality indirect feedback than direct feedback. Direct feedback usually is a better technique, has higher potential of reducing errors than indirect feedback. Non-energetic feedback is a word that we use if there is no power dissipation or energy storage in the feedback network. It's an important class of feedback amplifiers because in the previous course we have seen important properties that there is no deterioration of the noise performance, the drive capability, the energy storage, and the power efficiency by the feedback network. So all properties are fixed by the controller, and the feedback network has no effects on these parameters. This is not the case with passive feedback. If we apply passive feedback, then we are putting impedances in a series or in parallel with the signal path, and that will generally cause a deterioration of the performance. It gives power dissipation or extra energy storage in the feedback networks, and it gives also deterioration of the noise performance, the drive capability, and all those other aspects. So non-energetic feedback is of a better potential than passive feedback. Unfortunately, non-energetic feedback elements are only short and open circuit, transformers, and gyrators. So you can build a limited number of functions because for the gyrator there is no physical implementation. The transformer is not always very practical or large and expensive. Of course, with passive feedback that we are often going to apply, and we have, let's say, a level of acceptance of deterioration of the performance aspects. And it can be very low, this deterioration, if the feedback impedance is in series or the admittance is in parallel with the signal path are small, relatively small, than the impedances that are already present there because, for example, of source and load. So this is what we need to know in order to judge our solutions later, because what we want with structured electronic design is we don't want to, well, of course you can calculate and simulate everything, but we want to have good indication for the design which way to go, and therefore it's important to know properties and to rank them. This is a bit better than this, so let's say we can start with the best technique, and if that is not good enough, there's no solution. So let's do some examples of non-energetic feedback stages. So single transistor as controller and a non-energetic feedback amplifier with it. I want to show you a concept and I want to show you the implementation without biasing. We call it the signal path. A voltage amplifier with one transistor. Concept could be like this. We have a nuller. We have a non-energetic feedback with a transformer. We have parallel sensing of the voltage. You see the secondary winding N of the transformer is in parallel with the load. This generates a copy of the source voltage because the nullator nullifies the difference, which means that it should be, let's say, the voltage across the other winding of the transformer must be equal to Vs, otherwise the difference cannot be zero. And that is what the nuller does. It nullifies this difference. So this is a non-energetic solution. And this would be a practical one, a practical amplifier, just with a MOSFET as controller and the transformer as feedback element. More of interest today is a voltage follower. If we make a unity gain voltage amplifier, so we sense the load voltage and we need to compare, well, after attenuation, but it is unity, so we compare the load voltage immediately with the source voltage and nullify the difference. That would look like this. So the load voltage is compared with the source voltage and the nullator is placed in between. So the load voltage can only be the same as the source voltage. Now with the transistor, maybe you recognize we now have 3 terminal elements. So this gives a valid solution for a single transistor putting in, and here it is. And usually you call this stage a common drain stage, but the name common drain relates to the topology and not to the potential of the stage, which means it is a feedback version of the common source stage. And if we know about feedback, if we know in which way feedback changes the behavior, then we know immediately what the behavior of the CD stage will be. And we don't have to start and do all the calculations again in detail. A current follower is also an interesting stage for today. Let's see the current follower. Here we have a source current. We make the voltage across the source 0 and no current through the source. All the current is flowing through the output, and this is IL. So all IS is flowing to ZL, which means that the gain of this one is unity, which makes it a non-inverting current follower. And you can also place a single stage solution for a transistor in this one. Here we do. This is called a common gate stage. And maybe you did not yet realize that a common gate stage is nothing else than a feedback version of the common source stage. And if we know in which way feedback changes the behavior of the stage, then we can easily predict the behavior of the CG stage from the CS stage and what we call the error reduction capabilities of negative feedback. So passive feedback. Passive feedback, A means voltage in or voltage out. Passive feedback, this is the concept you probably know from the voltage and the non-inverting voltage amplifier from the previous course. And here we need a 4-terminal solution for the controller. You see there's no common node for the nullator and the narrator, so we need a 4-node controller, and here it is. We can use a differential pair for this. So this will be a single stage negative feedback voltage amplifier. B is voltage in, current out. The concept is like this. Hopefully you remember. And you see we have a three-terminal element. A three-terminal. The current IL is converted through YT, this feedback, into a voltage, a copy of the source voltage, and this difference is nullified. That makes it an exact copy. So IL relates to VS with YT. And here you see the implementation. It is often called a series stage. Some people call this source degeneration. This is focusing on the fact that the GM of such a stage in equal bias and operating conditions, width and length, will be smaller than the GM of a stage without feedback. But it doesn't stress all the other properties. As we know, it is a a negative feedback stage. We can tell you much more about other properties of the stage than only that it is a lower GM of a CS stage with the same dimensions operating on the same current. The concept C is a transimpedance amplifier, and you see we also can make this with a three-element with a controller with three terminals. It converts the source current into a load voltage, and here you see the solution with one transistor. And the last one, setting B, the parameter transmission parameter D, is a current amplifier. And here you see again that we have no common terminal for the nullator and the norator. IL, which is flowing through the parallel connection of Z1 and Z2, and therefore only a part of IL is flowing to Z1, makes that the part of IL an accurate copy is an accurate copy of IS because the voltage across YS is kept 0. And here is the implementation without biasing, of course, for a non-inverting current amplifier. So here you see these are passive, we call this passive feedback stages, single stage amplifiers having negative feedback.